So first thing I want to do is broaden the scope of the talk from the title. So as well as talking about light, I also want to talk about radar and about sound. And of course, light and radar, they're two kinds of electromagnetic waves, so they're the same kind of phenomenon, just different wavelengths. And then of course, sound is an acoustic wave. And the reason that I'm interested in these three different kinds of wave is because they've got lots of important applications. So, for example, light scattering properties of blood cells are used in the classification of the different kinds of cells in blood samples. Of course, everybody knows that radar and sonar can be used to detect objects like aircraft or submarines, for example. Another application of acoustic waves, of course, is in ultrasound to look inside the body. And also, light is important in measurement. For example, I'm working on an interesting project with Deb Kane and Doug Little in the Department of Physics to measure nanowires using their light scattering properties. But the main thing that I'm going to talk about today is applications of waves to climate. And the reason that I'm interested in applications of waves to climate is because, of course, there's a lot of concern around the world at the moment about global warming. And I think everybody's familiar with the basic principles. Carbon dioxide and methane are the greenhouse gases, and they're in the atmosphere, and they actually cause the atmosphere to warm. And this part's actually very well understood. But there's another part of this equation, and that is that warming due to greenhouse gases is in some part offset by a cooling effect, which is due to aerosols in the atmosphere. And it turns out that the actual magnitude of this cooling effect is very, very uncertain. And so this has been identified by the Intergovernmental Panel on Climate Change as one of the key uncertainties that needs to be resolved if we're to accurately predict future climates. So atmospheric aerosols, they're actually small particles. Their size is very, very small, from nanometers to a few tens of micrometers, and they're suspended in the atmosphere. And these aerosol particles, they may be from natural causes, for example, dust that gets whipped up by winds, or they may be from sea spray or smoke, or they could also be from man-made pollution as well. But the important thing, as far as we're concerned, is that they can absorb light, and that actually warms the atmosphere, or they can scatter light, and that has an effect of cooling the atmosphere. I'm particularly interested in mineral dust aerosol because this both absorbs light and scatters light. And so the big question is, does mineral dust, because it's got these dual properties, does mineral dust warm the planet or cool the planet? That's the big question that needs to be resolved. Now I want to show you some images of mineral dust aerosol. They're on the right-hand side. These are provided by my colleague Michael Box. Some of the features I just want to point out about this mineral dust aerosol is that it's got a very rough, irregular surface. Also, these different mineral dust particles are very different sizes and very, very different shapes. In fact, although no two particles are identical, they can be described by some stochastic description. So we can model them quite well, but each one is unique. So the long-term goal of my research is to answer this question: does mineral dust warm the planet or does it cool the planet? That's the long-term goal. But of course, this is a hugely challenging problem, very, very difficult problem. And some of the things that make this problem so difficult are that the mineral dust aerosol is a 3D particle with a very, very complex shape that's difficult to model. It's also made from a dielectric material which allows the light to pass through, but it's refracted as it passes through. This is another thing that's difficult to model. And the third thing is that these particles actually are random, as I mentioned, and this randomness is an additional complication that we need to deal with. So as is common through mathematics, probably the whole of science, the first step is to study a simpler model problem and try and understand what we can about this simpler model problem that's got some of these difficult features of the original problem but is a bit more tractable. So in fact, through this talk, what I'm going to do is I'm going to illustrate my research with a simple 2D acoustic scattering model. So I want to emphasize that this is not the focus of my research. The focus is to do this thing for 3D dielectric scatterers like mineral dust aerosol. But this is a simple model problem that's easy to discuss. So in the context of this simple 2D model problem, the big question is, do they warm or cool the planet? Actually, what we need to know is how much energy is scattered by these model particles. So the question becomes, how much energy is scattered? Now, in fact, techniques to answer this question have been around for a very, very long time. In fact, I can apply the straightforward techniques to solve this problem. And in fact, it takes 3.5 days to solve this problem. 3.5 days, this is terrible because this is 3.5 days for a very, very simple 2D problem. If we scale up to a realistic 3D problem, we're talking about weeks, months, years to answer this question. So the standard techniques are just not feasible. So this is a problem that I've worked hard on, and recently I've been able to answer this question using advanced techniques in 5 minutes. Okay, so there's a substantial saving. And so the rest of the talk, I'm going to talk about the revolution in the approach to scattering problems that lets us do this problem in 5 minutes instead of 3.5 days. So this is my model problem. What we've got is two model 2D scatterers, and they've got many of the features that we saw in the original mineral dust aerosol. So for example, these have got a rough, irregular shape. They don't look very random, but in fact I can introduce randomness into this model by perturbing the position and the orientation of these model particles. And then you see what I've done is I've illuminated these particles from below, and the red line indicates how much energy is scattered in every direction around the particles. And basically what we want to do is we want to add up the amount of energy that's scattered over all of these directions to come up with one single number that characterizes the scattering properties of these particles. So that doesn't sound too bad, but then the problem is if I illuminate the particles from a different direction, then the energy that's scattered is different. In fact, different direction, I get a different energy scattering pattern again. What's even worse is if I randomly perturb the positions of these particles like this, you see the energy that's scattered changes again. So I've got to find some way to deal with lots of different directions and also this randomness that's in the model as well. So in fact, the equation is very, very simple. Using the straightforward approach, one simulation of scattering takes 1.4 seconds. If I do this for, let's say, 1,000 directions to understand how it changes with direction, I've got to multiply that by 1,000 times. If I average over 216 simulations per direction, actually it's hard to do it in just 216, but let's say 216, then altogether this comes out as 3.5 days. So of course my job is to make this thing run more quickly, and I'm trying to do that by attacking all three aspects of this problem. So I'm looking for efficient simulation techniques that can do better than 1.4 seconds. I'm looking at techniques that can better handle having 1,000 different directions for the illumination. And I'm looking for techniques that can reduce the number of simulations we need to average out the randomness. So I'm working on all of these three things. But the thing I'm going to talk about mostly today is a way that we can do the simulation for 1,000 directions for the price of one. Okay? So instead of taking 1,000 times 1.4 seconds, I can do all 1,000 directions in 1.4 seconds. So to explain how I get this 1,000 factor improvement in the time, which brings us down to the 5 minutes I mentioned before, I need to actually say a bit about how scattering simulations work. Now, I think everybody probably thinks they understand how light gets scattered by an obstacle. So if we've got some ray of light comes in, it bounces off a bit like a ball would bounce off a wall. So we get some light gets reflected in this direction. And of course, it depends on the orientation of the surface. And if I choose a different direction, then of course the light bounces off in a different direction. Now, it turns out this is how light gets scattered by objects, but only if the wavelength of the light is very, very small compared with the size of the object. Okay? Now let me show you some model aerosol particles. These are kind of realistic size aerosol particles drawn to scale with the wavelength of red light and the wavelength at the other extreme of the optical spectrum of blue light. And what we see is that these aerosol particles are not very big compared with the wavelength. In fact, they're only a few wavelengths across. And for particles like this, the approximation of ray tracing type approximation doesn't actually work. In fact, the scattering behavior is much more complicated. Let me show you what I mean with an animation. So what we've got there is a wave that comes in from below, it strikes our obstacle, and then it gets scattered. And if you look carefully behind the obstacle, for example, there's some kind of, where you'd expect the shadow, there's actually some wave travels through there. And it's clear, even just with this simple demonstration, that the ray tracing type approach that we just talked about isn't what actually happens for this kind of small particle compared with the wavelength. So how did I do this simulation then if it wasn't using ray tracing? Well, in fact, the field that gets scattered is actually the solution of a partial differential equation. Now, I'm not going to get into the details of partial differential equations. Let me just say that actually electromagnetic waves like light and radar, they obey the Maxwell equations, and acoustic waves, sound waves, they obey the Helmholtz equation. From a mathematical point of view, these equations are very, very similar, and the same kinds of solution techniques can be used for both of these equations. So the details, I should kind of emphasize, the details are very, very different, but the broad techniques that we can apply are the same for both kinds of equation. Now, everybody knows that mathematicians, they like to write down a formula for the solution of an equation. So, for example, something like u is equal to sine x times cos y. That's the kind of solution that mathematicians like. Unfortunately, the Maxwell equations and the Helmholtz equation, they've only got solutions like that. That's only possible for a handful of different shapes of particles. So, for example, a spherical particle, various kinds of spheroid, a cylinder, a handful of other shapes, we can write down a solution like this one. Unfortunately, if the particle is not one of these shapes, then there isn't a formula that we can write down. We need to do some other approach. And of course, you've already seen that the mineral dust aerosol that we're interested in isn't one of these simple shapes that we can write down the solution for. So we need to do something different. And the different thing is that we're going to compute an approximate solution using a numerical technique. And the branch of mathematics that's concerned with numerical solution of equations is called computational mathematics or numerical analysis. And the main concerns of someone like me who's a computational mathematician are firstly to compute an algorithm, so to develop an algorithm and perhaps associated with that a computer program that can approximately solve this differential equation. The second thing that I'm concerned with is some kind of mathematics that analyzes how big the error is going to be when we use this numerical technique. Now, I want to be really careful about this part. I don't want to give the impression that the approximation is like 3 is an approximation to pi. That's not what I'm interested in at all. For example, when I approximately solve a partial differential equation, it's no big deal for me to get error that's 10 to the minus 8 or better, okay? So to give you an idea, an approximation to pi that's accurate to 10 to the minus 8 is this one. You see, the blue digit marks where it's first different from pi. So this is actually, for all intents and purposes, as good as a formula. This is a very, very accurate solution that we're developing. The thing that I really want to talk about this evening, though, is this third part, which is an analysis of the complexity of the algorithm. In other words, how long does it take and how much memory does it use? And in fact, understanding this part is the essential thing to understand. And the thing that I want to kind of get across is it doesn't matter what numerical technique I use for solving the wave scattering equations, we end up with a system of simultaneous equations. So what we've got there is a system of 2 simultaneous equations for 2 unknowns, x and y. And probably most of you will have seen equations like this in high school and will have solved equations like this in high school. And in fact, numerical techniques for solving partial differential equations produce simultaneous equations like this, but with maybe thousands of equations for thousands of unknowns. So to solve systems of simultaneous equations like that, we use a computer. And there are actually broadly speaking, there are 2 different kinds of algorithm that we can use to solve these simultaneous equations on a computer. This is a whole talk in itself, but very, very briefly, there are direct solvers, and the advantages of a direct solver is that we can solve many, many equations for the price of 1. The disadvantage of a direct solver is that it uses lots and lots of memory, okay? The other type of technique we can use is an iterative solver. Iterative solvers need generally less memory, and they're generally quite fast, but the problem with them is that you can only solve 1 equation at a time using an iterative solver. So given that I want to solve for 1,000 directions at once, it's clear which one we want to use. We want to use the direct solver because of this property we can solve many for the price of 1. Now, it turns out that when we solve systems of simultaneous equations, the amount of memory that we need if we use a direct solver is proportional. So if we've got n equations, it's proportional to n squared. So what that means in real terms is if I want to solve 10,000 equations, then I need 1.5 gigabytes of RAM to solve this problem. Now, my old laptop, that is my old laptop there, that's got about 2 gigabytes. So my old laptop can just about solve this problem with the operating system and a couple of emails and things built in. It can solve this 1.5 gig problem. That's about as high as it can go. If I want to go to 30,000 equations, then I need 13.4 gigabyte. That's very difficult, actually. Luckily, I asked my wife if she'd buy me a new computer a few months ago, and she let me get the 16 gig memory upgrade. So, in fact, I can solve these kind of problems quite comfortably now. But if I want to solve with 100,000 unknowns, then I need 150 gigabytes. Now, things are getting very difficult now. For 150 gigabytes, we need some kind of high-performance computing platform. In fact, this machine is the one that I use for most of my computations. It's called RA. It's owned by the Golden Energy Computing Organization in the US, and it's an absolutely fantastic machine. If we want to go even higher again and solve, say, 2.5 million equations, then that's 9,300 gigabytes that we need to do this. RA can't do it, actually. In fact, very, very few machines, even if you look at the top 500 supercomputer list, very few machines could use a direct solver for this kind of problem. So if we want to use a direct solver, we've got to keep down to 100,000 type number of unknowns. We can't go higher than that. So now this is, in a way, this is the most important slide in the whole talk. This is where everything happens, actually. This is where the revolution has happened in scattering algorithms. Because if you go back, say, 10 years, then the state of the art was what's called low-order algorithms, something like method and moments. And algorithms like this one need millions of unknowns to solve the kind of scattering problems that I'm interested in. And of course, with millions of unknowns, it was true 10 years ago, it's still true now, you need to use an iterative solver to solve these equations, and you can only do one at a time. The revolution happened in, let's say, 2004, when Ganesh and Ivan Graham published an algorithm for 3D acoustic scattering. This high-order algorithm that they published can solve these problems with tens of thousands or maybe hundreds of thousands of equations. Okay, so this is very much in the realm of what can be tackled by direct solvers. After Ganesh and Graham published this work, Ganesh and myself, we worked on similar high-order algorithms for electromagnetic scattering, and in a series of papers through 2006 through to 2009, we produced some very good algorithms for these kind of electromagnetic problems. And then my recent work is not published yet, but Ganesh and colleague Darko Volkov, we've produced a similar high-order algorithm for dielectric scattering. And this new algorithm is the algorithm that we need to tackle the mineral dust aerosol problem in 3 dimensions. So I want to show you a simulation that we did using our dielectric algorithm. This is simulation of light being scattered by a raindrop, and the purple colours is the light outside the raindrop. And one of the beautiful things, I think, is that the light actually passes through the raindrop with some refraction, and you can see the light passing through the inside. It's in the green colour there. I mentioned that we were attacking all fronts of this problem. In fact, I'm not going to say a lot about that tonight, but I do want to mention that we've done lots of work recently on these other aspects. So we've worked very hard at dealing with what happens when the particles move around or when they're rotated. We've done a lot of work dealing with multiple scattering. So myself and Ganesh, and with Ralph Hittmeyer as well, we've got several publications in this area. More recently, we've been looking at reduced basis methods and also advanced techniques to deal with the randomness, so generalized polynomial chaos methods to deal with the randomness. None of this work is published, but we've got a couple of new papers on this that hopefully they'll appear soon. So let me come back. I talked about this 2D model problem. I said that we wanted to say how much energy gets scattered in all directions. I didn't answer the question yet, so now let me answer the question. We used 216,000 simulations on the supercomputer Ra. It took 5 minutes. I mentioned that part before. This curve shows the amount of energy that gets scattered, so the total amount of energy that gets scattered as a function of the direction that the illumination comes from. And you see that it's not much gets scattered from the end on, but quite a lot gets scattered from the broadside direction. If you've got sharp eyes, I'm not sure if it comes across very well, but this line is actually surrounded in places by some shading. In fact, the red line is the expected value for this amount of energy that gets scattered. It depends on a random variable, so the true value that we observe in practice might deviate from this. And the shading gives an idea. It's plus or minus 1 standard deviation, so it gives us an idea of how much uncertainty there is in the amount of energy that gets scattered. And this picture uses all of the techniques that I mentioned on the previous slide. So I could talk for hours about this, but I think it's probably good that I summarise. So I hope that I've shown that mathematics, and especially computational mathematics, is important for the understanding of lots and lots of important problems, including the problems of the climate that I'm interested in. We've developed several important tools over the last few years that we plan to apply to understand mineral dust aerosol and its scattering properties, and of course our goal is that that will be carried forward by climate scientists to lead to improved climate models. I want to finish by just saying that this work's not, it's done in collaboration with other people. So I'd like to thank my collaborators, Ganesh, Michael Box, Ralph Hittmeyer, Darko Volkov, and Deb Kane and Doug Little. I think they're here this evening. So thanks very much, everyone. If anyone would like more information about my research, then there's a bit more on my website.